Okay, the next slideshow has got to do with so-called polymorphism. That's a big name, sounds very fancy. Morphism is a kind of behavior, for example, and poly means many, so many different kinds of behaviors. So I'll try to explain what it really means. Some of the topics we have to talk about now are the following. Pointers to base classes. You know what a pointer is, you know what a base class is, so a pointer to a base class is a pointer to a base class, so that should be fairly obvious. Basically what we want to do is, when we have a pointer to a base class, call one of its member functions. But are we really talking about the member function in the base class or in its derived class? There are two scenarios, and this leads to polymorphism, because the base class pointer can point to any of its derived classes at runtime. So let me just draw a little diagram visually before we start going into nitty-gritty C++ code. So I'm going to, in a nutshell, I'm going to explain what I want to do here. So here's my base class B. I've got two derived classes just for convenience. Let me call the derived classes D1 and D2. So there we are. Now a pointer to a base class, I will draw it as a pointer. You know what a pointer is. And I've got a function, for example, f. And let's say for convenience I have a function, the same kind of function f, defined in derived classes. So when I have a pointer to a base class, I can call the function f as is, of course, but the pointer may actually can be assigned to the address of a derived class, and the question is that the pointer is really pointing to the address of the derived class object. Does he call the function f at this level, or does he call it here? It depends what you want. Each is possible in C++. In the previous section you saw that the base class, which was not defined as being a virtual function, he would just call the base class function. So we have different options. That's what we're going to be doing now. We have abstract base classes. Sometimes you can have abstract base classes B here, where you cannot create objects of the base class. And we see what the implications are. And finally we will discuss what the correct canonical header file is. What's the minimum HTTP file you need to create for a class? So here I'm taking the same example as before. I've got a base class account, which we talked about. We have a derived class called credit, and let me just create the following. It's all for free. I've got an account object, I've got a credit object, and I can say the pointer AC is equal to the address of the CRT object. So it's the credit, it's the address. There are other possibilities in the moment, but I won't discuss them yet. So assigning a credit object to the address of account to the base class is not possible, because it's the wrong is-our relationship. Now, if I got function visibility, we have pointers to base classes. So I've got a credit object, which is an object of a derived class. I've got a pointer to a base class, and I've got the I can assign it to the address of the derived class. That's fine. So the pointer is really pointing to the account. When I say display ACN, the compiler sees it as being an account, so he calls the function in the base class. Even though the pointer is pointing to the address of CRT, so if I call a member function on the CRT object, it won't work because he doesn't know where he is. So if I go back to my diagram, what's happening here in this particular case, or this scenario, is even though I've got my pointer here to the base class here, which is account, and it's the pointer is pointing to the address of the derived class, he still doesn't go down one deeper, as it were. He hangs here because there's no runtime information, you see. That's the problem. It's not a problem, it's a feature. Now, sometimes, well, okay, to motivate polymorphism, I want the following. Instead of the, as it were, the function hanging here, in other words the pointer hanging here, so that when you call the function, you call the function in the base class, I would like to, depending on the derived class address, call the derived class object here or here. So polymorphism That's what we want to do. So basically, similar objects respond differently to the same message. We talked about the object-oriented way of programming. We got messages. So if the pointer is really pointing to D1, it'll call the function f in D1 automatically, and if it's pointing to D2, the pointer that is, it will call the function f here in D2, and it'll switch automatically, something you don't have in MATLAB or possibly or in C and so on. So you have to do the switches yourself. So in other words, depending on where I am, if I got a pointer to a credit object, I want you to call the display function in credit class, and if it's a pointer to the address of a savings object, I want you to call the display function in savings. Now, what's the big deal? If I want to achieve this kind of runtime switchability, let's say I declare my display function in the base class to be virtual void, in the header file only. So you can only you only have to tell the compiler once that it's virtual. So if you put the virtual keyword in the CPP file of account as well, it'll give a compiler error. So you only have to say it once. It's a keyword, and then you're finished. So when I get the following, so in other words, when I call the let me go back to my diagram again. When I got my pointer to the base class, and the pointer is assigned really to the address of the derived class, he will call the function here, which is what we want in this particular scenario. Now, the virtual function in this particular case may be overridden. You don't have to. If you do not override the display function in the derived class, when you call the function, he will call the function in the base class. So it takes default behavior basically. Yeah? Okay, how do I use polymorphism? So we have again this setup. We've got a pointer to an account, which is the base class. We've got a credit object. We can now, for free in C++, assign the pointer to the address of a credit object. When I now call the display function on the account pointer, he will call the display in credit and not the display in account. So you're really pointing to the credit object, so call the display on the credit object. That's what we want, and this is polymorphism. This pointer can be changed to a pointer to some other kind of object at runtime, and it will switch, and it will call, depending on the address he's pointing to at runtime, he will call the correct display function. So that's polymorphism. Okay, so this is default behavior. So in other words, you do not have to override the virtual function when you go to derived classes. This is in contrast to the last major piece of syntax we want to talk about, and these are pure virtual functions. These are abstract functions. They've got no body in the base class. It's like an interface or a protocol or a specification, which we already have talked about. And the base class is account, and the withdraw function is withdraw, and the amount is the input here. Equals 0 means it's got no body. So an abstract base class, as the account is now called, an abstract base class is one which has at least one pure virtual member function, of which this is an example. And the consequences are that you cannot create an object of an account, because you can never call this functions, because some of the functions are empty. It would be nice if you just make a class with empty functions, and you get something for free. So this defines an interface. The consequences are that here the account, every derived class from account must implement the withdraw function, otherwise you get a compile time error. He says something like unable to create instance of abstract class, which is fair enough. So because if you do not implement the withdraw function, override the withdraw function in the derived class, this function here will be inherited, of course. That's inheritance, and it's a pure virtual function which is inherited, and it makes it pure virtual in the derived class, which makes the derived class abstract, and abstract classes cannot have instances. So it's a to summarize, an abstract class defines an interface. It's a base class with at least one pure virtual member function. The consequences are that the ABCs have no instances. They're just base classes or holders for concrete classes. However, you can create a pointer to an abstract base class and switch the pointer from one address of a derived class to another address of another derived class. And of course, the derived classes must implement the pure virtual member functions, otherwise they will be seen as an abstract class as well. So that was a whole mouthful, and we're finished with the pure virtual functions. So it's a bit of a design problem when you're actually developing applications with base classes and derived classes. Do I create a default virtual function or a pure virtual function? It's a bit of design. Default virtual is when you don't care. So in other words, default behavior is okay. So if you want to overrule it, you may. It's like a hook. And pure virtual functions have to be overruled. Last but not least is the concept of the virtual destructor. There's a problem with inheritance in general. If we have the account class and the credit class, and both of the destructors are non-virtual, just normal destructors, and let's assume that we're in we've got some heap memory in each object, each class. If we do the following, you see here I got account star a new credit. Of course, every new has to have a delete, as we've seen before. When I delete ACN, it only calls the destructor of the account. So let me go back to my original diagram. So when I've got a pointer here into my base class as always, or in this particular case, when I delete my base class pointer, you should clean up memory. But where is memory? Memory is in B and D1, for example. So when you call the delete, all he does is call the destructor of B and delete the local memory in B, but not in D1. So you've got a memory leak. So in order to avoid this particular situation, we have to declare my destructor as being virtual, and the way we do it is as follows. In the base class we say it's a virtual destructor. Its last remarks are, it's not necessary to declare virtual in derived classes, but it's advisable. But you can do it, it's not necessary, it's okay. So once you have a virtual destructor, he builds a runtime virtual table and everything is okay. So that's just basically the rule is, if you've got base classes and all sorts of memory floating around, just use virtual destructors. Summary. So we give, this is an example of so-called subtype polymorphism. A subtype polymorphism has got to do with the fact that you've got a pointer to the base class, and it's the pointer can switch between derived class addresses, and when you call the functions, the correct function is called. We distinguish between default virtual functions and pure virtual functions. A powerful feature is the principle of substitutability. It means the following: if you've got a function which expects the address of a base class, you can always call the function with the with an object of a derived class because of the polymorphic functions. Last remark about the about virtual functions. Let me take the virtual function here. There was an example. Yeah, here if it's implemented in derived classes. It depends on the situation, but in general, calling a virtual function is about 10 times slower, less efficient than calling a non-virtual function. Now this doesn't have to be a major problem, because if the function you're calling is a big algorithm, it takes I don't know, 5 minutes to run, and the call on the virtual function is minimal. But if you're calling a virtual function which gets called many times during your program, this is going to give problems. So it's something you need to know about. And the last remark is, all of this virtual stuff, this is really object-oriented stuff. It's not as popular as it may have been in the past, because we've now got templates, and we will have so-called parametric polymorphism in template classes, template programming, also known as what's called parametric polymorphism. But it's compile time, and it's much more efficient, but less flexible. The advantage of subtype polymorphism, as it's called here, is that you can switch at runtime between different pointers to different derived classes. So if you want flexibility at possible speed cost, you use polymorphism here, subtype. Final remarks. We give some things to watch out for, basically. Some guidelines to promote the correctness of the code, the efficiency and the maintainability of these software systems. So many developers have learned all of this the hard way. In the 1990s and 80s, object-oriented was the new religion, let's say, and everybody was an object-oriented guru or object-oriented programmer or something, and it went a bit overboard. But one of the biggest problems was that people used too much is-a, in other words, hierarchies and inheritance, and not enough has-a, which is composition. In the next sessions we'll be discussing parametric polymorphism, which is compile time polymorphism, using templates instead of subtype polymorphism, which will be much better. Okay, so what's the first problem we have to you have to worry about? Semantic correctness of class hierarchies. Since we talked about it a few sessions ago, since classes are context sensitive, they change all over the place. So when something changes, all its dependents change. So if you've got a base class, its dependents are its derived classes. So you'll get a whole avalanche of changes between base classes and the derived classes. Things tend to be very volatile as more functionality is added. And yeah, if you say inheritance, you inherit everything. In other words, the derived classes get everything. And in the past we've seen the maintainability problems involved with inheritance hierarchies, and certainly not multiple inheritance. You can derive a class from 2 or more base classes, so this is really out. I never liked it anyway. Okay, one of the issues is efficiency. So as I've said, virtual functions are about 10 times slower than non-virtual functions. It depends on the relative times it takes to call the function and actually execute the function. So if it's a big algorithm, it doesn't really make any difference. But the reason for the virtual functions being more inefficient is that you've got an extra pointer to a method in the virtual function table at runtime. So it's got to be searched for. The function call overhead may then be significant. It depends on the level of granularity in which you're using it, of course. And yeah, inline virtual functions, the optimizing compiler may not be able to inline the virtual function, so you've got a problem. Okay, so that's more or less it. Okay, here's an example. Think about the following hierarchies. I've got two-dimensional shapes, so the base class is a shape. It's got derived classes called circle, polyline, and so on. Financial instruments, so you have a base class, you might have derived classes for options and bonds and so on. One-dimensional data interpolators, so you've got different kinds of interpolators in fixed income applications, for example, linear interpolation, spline interpolation, what else? Akima, Hyman, and so on and so forth. So what are the virtual functions? In other words, the default virtual functions and the pure virtual functions. So that's a tricky one. Why is the principle of substitutability important? How many abstract classes can you find in computational finance? I've given you one, instrument possibly. And what are the abstract methods? The abstract classes correspond to, I suppose, the superordinate concepts in concept hierarchy. So that's a bit of a hint for you. Can a default virtual, okay, I got in a base class, I got a default virtual function. Can it call a pure virtual member function? So I've got a default virtual function, default virtual with a body in the base class. In the body of the function, can it call a pure virtual function? In other words, a pure virtual function is one which in the same class is defined as being abstract, but in derived classes it does have a body. Okay, so let's give a demo. Very simple example. I've got a payoff hierarchy, so I'm creating a hierarchy of payoffs. The payoff could be used later in option pricing formula and so on, because the or an initial condition and finite difference method for option pricing. Okay, so here's I've got a project. Yeah, people are testing my network at the moment. Okay, so I got a project. I've got a payoff, which is a base class. I got a call payoff, which is derived class. Later on, you could have put payoffs and so on. And I've got a test program. And let me just go to my my HPP files first of all. So I've got a base class called payoff, and it's got the usual stuff. So this should be all familiar by now, with the possible exception of the virtual function here. You see, it's got a function called payoff. It's got a double as input, double S. It's a const member function, of course, because it's not changing your member data. And it's virtual here, so it's a pure virtual function. Derived classes must implement it. And how do I do it? In my call payoff, it's very simple again. My call payoff is derived from the payoff base class. Of course, call's got a one factor call, have a strike price, and you've got all this stuff here, get and set functions, and basically I have to implement my payoff function with a double as input, and so it's got a const, right? If I look at my body, it's all the standard stuff. So here I've got the payoff. If s is greater than k, I can return s minus k, otherwise return 0. Now in STL later on I can just say max s minus k 0, so the max of s minus k and 0. Here's my test program. So I create a pointer to a payoff. Here's my base class pointer. I can assign it to the address of a call payoff using new, of course. Here's my strike price 10, and I want my payoff to be 20. So when I work this out, it should be 20 minus 10, so you get 10. I delete my payoff. Now I build my payoff again. Now we're at the money, so the strike price is 20, and the value I want the payoff at is 20. So it should be 0. Again, I delete my payoff. So if I run my program, so I get 10 and 0, which is what I predicted. Okay, so this is a very simple example to show you how pure virtual functions work. And why have I made it pure virtual? Because there's no idea of a common base class payoff function. Every derived class is different, so every derived class has to do it in its own way, so it's only an interface or a protocol. This is a very simple example you might see in some applications or books and so on, but it's just it's a toy example, but it does give you a good idea of what's going on. It is very powerful because later on we'll be talking to payoff functions from solvers, and we don't care what's in the body. It's just a runtime pointer to a base class, which is very nice. Okay, so you can add your new classes using this technique. So we'll take a break now. We're finished with the super duper polymorphic inheritance stuff, and we'll stop now for the moment, and we'll see you later. Bye.